A function y is given as sine inverse of 2x by 1 plus x square, and we need to identify the points where the function is non-differentiable. The function y which is given as, that is f of x, given as sine inverse of 2x by 1 plus x square, has different forms of definition. By definitions of inverse trigonometric properties, it would be minus pi minus 2 tan inverse x if the value of x happens to be less than minus 1, and when the value of x is between minus 1 and plus 1, then this is simply 2 tan inverse x, and when x is more than 1, this function would become pi minus of 2 tan inverse x, right? Now once f of x is defined piecewise, let us even find the derivative of the function again piecewise, and then we will check the differentiability at the breakpoints. Otherwise 2 tan inverse x is differentiable, pi minus 2 tan inverse x is differentiable, minus pi minus 2 tan inverse x is differentiable. So the question of differentiability comes only at minus 1 and plus 1. So let us check whether it is differentiable at those points or not. So what is derivative f dash x also defined piecewise? This derivative would be minus pi 0, so that the rest of the part it is minus 2 by 1 plus x square if the value of x is less than minus 1. In between minus 1 to 1, the function is 2 tan inverse x, therefore the derivative is 2 by 1 plus x square when minus 1 is less than or equal to x less than 1, and in the last case when x is more than 1, yes, pi derivative is 0, minus 2 tan inverse x derivative, that is minus 2 by 1 plus x square. Now we have f dash x also defined piecewise, and as we decided, we need to verify the derivatives at the minus 1 and at plus 1 where there is a break. So if you observe in this, what is f dash minus 1 minus, that is when x is less than minus 1, right? Then the derivative becomes minus 2 by 1 plus minus 1 whole square, minus 2 by 2, this value is minus 1. So we are able to identify the left hand derivative at minus 1. Can you identify the right hand derivative at minus 1? Yes. Then the function will go into minus 1 to 1 domain, that is 2 by 1 plus x square, that is plus 2 by 1 plus minus 1 whole square, 2 by 1 plus 1 whole square, that is 2 by 2, which is 1. So what did we observe here? The left hand derivative at minus 1 is minus 1 and the right hand derivative at minus 1 is plus 1. So what is conclusion from these two? At x equal to minus 1, f of x is not differentiable. So that makes us C could be a valid option, but only provided this is the only non-differentiable point. So for that, what are we supposed to do? We need to verify at 1 also, because at 1 also there is a break. So for that, what we do? We calculate f dash of 1 minus, that is to the left side of 1. How is the derivative? Yes, it is 2 by 1 plus 1 square, that is plus 1. Now when we calculate f dash of 1 plus, that is derivative on the right side of 1, the derivative is minus 2 by 1 plus 1 square, which is minus 1. Now what do you observe here? Yes, at 1 the left derivative is 1 and the right derivative is minus 1. So from these two observations we conclude even at x equal to plus 1, f of x is not differentiable, right? So now what would be the proper option? Yes, it is not differentiable at minus 1 as well as plus 1. So the function is not differentiable at both plus 1 and minus 1. Now as we have a much better practice on drawing the graphs of these functions, maybe the calculation of left hand derivative and right hand derivative is also not required to identify the differentiability. If you can draw the graph of y equal to f of x, how does it look like? On the Cartesian system, when we wanted to draw the graph of f of x when x is less than minus 1, then the graph would be starting from infinity, but by the time we reach minus 1, it would stop at minus pi by 4. Then, how will be the graph between minus 1 to plus 1? It's simply 2 tan inverse x. So from minus 1 to plus 1, if you observe the graph, it would be passing through origin, because at x equal to 0, it would be 0, and it would be a curve passing through origin up to plus 1, it will go up to pi by 4, and after 1, again the graph would be falling towards x-axis and it would tend to infinity. Now if you observe it clearly, at this point minus 1 and at the point 1, there is a sharp edge. So at x equal to plus 1 and at x equal to minus 1, the graph of y equal to f of x has sharp edge, and if a function has a sharp edge, it is continuous but it's not differentiable. Therefore, once we identify the graph, even there is no necessity of calculating the left hand derivative and right hand derivative. It clearly says where there is a sharp edge, the function will have non-differentiability. That is also the conclusion that we can reach, right? So once we are familiar with graphs, we can directly draw the graph and identify the differentiability of the required function.